Very good afternoon, and thanks for being here. Over the last few days, we've heard some excellent presentations about what quantum computers can do for us, the big potential with it. But at the same time, we've also heard about the big challenges we still need to solve to be able to make practical quantum computers. And especially being highlighted now are issues around integrating quantum computers with HPC centers. That means you have quite high performance requirements for your quantum computers, and at the same time, high uptimes. Let's remind ourselves, why do we need quantum computers? We need them to solve problems that we cannot solve with the classical computers. And we also know that we will need lots of physical qubits to build practical quantum computers. Estimates range from hundreds of thousands of qubits to tens of millions of qubits. And that's really due to the fact that the qubits have a lot of noise and errors inside them. So it can take upwards of 1,000 qubits to make one logical qubit. And of course, these estimates are based on who you speak to, what kind of algorithms you're trying to use, and of course, many times also like the time of the day. But one thing is clear, that from where we are now, we will need a lot more qubits to build practical quantum computers. And all these qubits, all these physical qubits, millions of them, will have to be in a perfect state of tune all the time. The place we are right now is that with the current control methods, we know that it takes at least 3 to 4 experts to be able to control even a 10-qubit quantum computer. And as you can see from this photo, they don't look very happy because it's a pretty tedious job and is not fun to do. So if we would just do a simple extrapolation based on where we are right now, and we need to build a 10 million qubit quantum computer, which we will need, you could end up with 3 million people. So of course, probably it'll be a bit less, but it's going to be a lot of people. And this does not scale because it's very hard to train quantum scientists. It takes about 30 years to train them up from the time they are born, and that too only if they're interested in quantum mechanics, which is not always a given. Slow tune-ups are already hindering the development of quantum computers now. When we speak to scientists in different parts of the world, a few months ago, I had the good fortune of meeting Professor Yonuk Chung, and he said that, Vishal, they could quite easily fabricate like a chip with 100 qubits, but the reason they are not doing it because tune-up times are so long that it's really not worth the effort. And that also is having an impact on the characterization of the qubits. And as you know, that in order to do your chip development, you need to characterize the qubits, and many times a lot of the characterization steps need your qubits to be in kind of perfect tune. And because the characterization steps are long, that means your kind of chip development kind of times are long because of all the iterative development. So if you can reduce the time of tune-ups, you can reduce the characterization time, and hence you can speed up the chip development time. And that, of course, has an impact on how fast we can get to practical quantum computers. Will it be 10 years? Will it be 5? Will it be 15? Is all dependent upon how fast you can do the device characterization. So what is, or what's the reason why keeping qubits under control is so hard? So let's just go back and remind ourselves on the differences between the classical computers and practical quantum computers. In the case of classical computers, if you want to control bits, it's actually quite straightforward. You just turn the flow of electrons on and off. So you have a switch. If it's closed, then the electrons flow, you get a 1. If you open it, electrons stop flowing, and you get a 0. Whereas in the world of qubits, you're trying to manipulate an actual quantum particle. They can be natural quantum particles like you use in the case of spin qubits, or it's an artificial atom like in the case of transmons. In all the cases, what really happens is that because qubits are so small and with a very small amount of mass, they get affected by anything and everything around them, including thermal radiation, cosmic radiation, and so on and so forth. So in other words, if things are small, they will get tossed around much easier. If they are big and heavy, they can't get moved around. And from our daily experience, if you put a 1-ton an iron ball in a hurricane by the beach, it's not going to move. But if you put a kind of ping pong ball there, it's just going to get tossed around. So in other words, if you are a hurricane, your life feels, if you're a qubit, your life feels like a hurricane. So your daily experience is something like this. But what you're really trying to do is keep still and not get tossed around with all the strong winds coming from all sorts of directions. One way to do that is to get some jets of air over and below, and through these jets of air blow very high pressure air, so that when you have the buffeting of the air coming from one direction, you're able to kind of push the air pressure from the other side to keep the qubit in state. The analog, of course, here is the ping pong ball is our qubit, and these jets of air are electromagnetic pulses. But also we have to remind ourselves that these things have to be individually controlled. I mean, each kind of jets of air to all the compressors. So you end up with, for every millions of qubits, you will end up with tens of millions of electromagnetic kind of pulses to keep it in state. However, we also know that you can't build a quantum computer with one qubit. You will need a lot of them. So your world will look a bit like that. And this, without even knowing any theory behind qubit control, you will realize is not possible for humans to control millions of these things at the same time. So therefore, you need to do something else. The software tools that we have right now at our disposal to be able to do the automation are not really up to their job, because a lot of different things need to be done. To give you a perspective on what your typical quantum scientist needs to take care of, includes everything from choosing what experiment to do, performing those experiments, visualizing the data, analyzing the data, managing the data, and of course sharing the data with the lab and the other collaborators around the world. And what they have at their disposal for this very complex task is some sort of a Jupyter notebook. So to do an experiment, they write some code, do an experiment, write some code, do some analysis, write some code, draw a graph, and so on and so forth. And then this all is coupled by a bunch of other windows that are there to be able to control all the instruments that are connected to your quantum computer. So it's not unusual to walk into a lab and see people jumping between 30 plus windows to keep their quantum computer under control. So, and all these activities will require a lot of manual effort. The impact of that is on speed and accuracy of the work that they do. And as the qubits go up, experiments become exponentially more difficult, and you're just basically stuck, right? So it just becomes very hard. So that's why we need automation. In late August, earlier this year, we launched Quantum Edge, our first product. And the goal of that was to bring in fast, precise, and automated qubit control. Now, if you want to use a Quantum Edge, you'll see benefits in two ways. One is Quantum Edge brings a bit-like stability into the world of qubits. And what I mean by that is that if we just remind ourselves how how bits behave, is if you give some current to your chip, you get these kind of noisy square wave pulses, and on top of that, you'll apply some, let's call it bit cleanup layer, mixture of hardware and software, and you'll end up with some very clean square waves. And these square waves are always very stable. So in our daily experience, if you have your regular computer, you put the power on, you can go away and come back years later, your quantum computer will always, your classical computer will always stay in state because your bits always stay in state. So that's the level of stability we are used to. But in the world of quantum computers, as I had mentioned earlier, your qubits are always constantly in a storm. What Quantum Edge does is brings this stability through automation, which gives a feeling of stability to the upper layers. So your error correction layer will really see the qubits to be in a Zen-like state so that it can start to do its job. And the benefit of that is, of course, that the amount of overhead from the error correction layer will be dramatically reduced if you use our software. The second impact is we've also used Quantum Edge to bring a new paradigm in the ease of use of how to control quantum computers. So where that manifests itself is that as a user of Quantum Edge, you'll see your world shrink from 30 plus windows to be managing your quantum computer to one integrated user interface. And in that user interface, you will have QPU monitoring, you will have automation workflows, and also all the data visualization. And it comes pre-integrated with the major control hardwares of the world. And I'll talk a bit more about that. Next, I'll share some kind of windows of the Quantum Edge software to give you a feeling of its ease of use. So if you log in into Quantum Edge, what you will see is an overview of your topology of your qubit. And what we've done is made a lot of effort to do it in a way that the moment you glance at it, you get a good feeling of the state of the quantum computer. Is it good to use or it's not? Out here, you can see the gate fidelities of the various chips. You can change it from the drop-down menu to review T1, T2, or any other values of interest. But at the same time, it's also important to mention that from the scalability perspective, the software has been designed to be highly scalable. So whether you have a 5-qubit chip, 100-qubit chip, 1,000-qubit chip, or beyond, it's within the capability of the software to manage the tune-ups. The only question is, do you have enough control electronics? If you were to click on any of these qubits and zoom in, you can go and see more details around the data. And in this case, the Rabi experiment has been highlighted, so you can see the graph. And at the same time, on top of that, if you were to kind of scroll up, you should be able to see your qubit spectroscopy, scroll down, single shot readouts, and so on and so forth. If you click further, you can look at the data table, which you can download and use for some other experiments. Moving down further, you come to the qubit workflows. This is really the heart of what we do. So what you see here is a single qubit workflow, full end-to-end, all the way from resonator spectroscopy, qubit spectroscopy, Rabi, Ramsey, and ending in the single qubit randomized benchmarking. And one of the benefits of this software is that it comes basically built in with this workflow. And if you want to do the editing of the workflow, you can do that. And in the future, we are also working to add the ability for you to add your customized workflows here. And then there's the speed factor, because you don't need to learn how to use the instruments. They come pre-integrated. All you do is press the icon, and the whole process starts. If you want to do your qubit spectroscopy, one of the fundamental experiments, it'll take about 15 seconds. And the entire single qubit randomized benchmarking will take 50, 60 seconds. Of course, that is dependent also upon the level of accuracy. So it could be a bit longer, it could be a bit shorter, but that's the typical time you're looking at. Similarly, if you just go down, you still see the topology of the qubit. You can choose whichever workflow you want to look as those workflows are going on as we go forward. On the data visualization side, you can click down further, and here you see the graph for the qubit spectroscopy. And what we've done here in this screenshot is kind of chosen qubit spectroscopy for qubit 17, if I can see it right from here. And so that gives you a comparison of the multiple runs on qubit 17 for qubit spectroscopy. And as far as the graphs are concerned, they are very interactive. You can zoom in to look at more detail, or you can zoom out if you want an overview. Also, these graphs are downloadable if you want to share them, make them for your reports, and so on and so forth. Similarly, you have your Rabi experiment, same thing. You can compare the different Rabi experiments that you've done. You can move on and look at your single qubit randomized benchmarking to single shot readouts, and so on and so forth. Now, one more factor to remember when we were building Quantum Edge, that from day one, it's been developed with an actual quantum computer. So we've been developing our software by renting the lab that Blue Force has in Delft. And inside that dilution fridge, there are 2 QPUs from Quantware and control electronics from QBlocks and quantum machines. And why did we do that? Because for us, it was very important that from the time we launched the software, it is making benefits to the wider community from day one. We've already had the opportunity to go to multiple labs around the world where the typical time it takes for us to just go in, deploy our software, and get the whole system automated is in the order of 4 to 6 hours. So it's actually quite fast if you really want to try our software on your system. This is a list of systems that we already support. That's Q-Blox, quantum machines. We will have support for Zurich Instruments sometime early next year. And then, as I mentioned, the QuantrolOx chip is being used, and we've tested the software with up to kind of 10 qubits right now, and should keep working. And we'll love to try it on any of your QPUs. As I conclude, I would like to add that one of the things that we really want to be able to do for the community is really give the choice to your organizations, to your labs, to be able to choose the right components to develop your quantum systems. Because as we are seeing that the industry is moving so fast, our needs are evolving. And what we guarantee as Quantum Edge, that no matter what components you choose, we will ensure that this entire workflow can be automated to improve the productivity, to allow us to get to quantum advantage soon. With this, I'll end my presentation. Open to questions. If there are no questions, then you're most welcome to visit us at our booth, and we'd love to learn how to deploy our software with you.